Welcome back for some more Algebra 2 Semester 2. I'm Mr. Who. We're talking about Skill 16, which is exponential functions. Now, you may have seen them before or heard of them before, but they are a very interesting type of function and one that's very useful in the real world when people are modeling. When many different fields model using this exponential function, okay, they usually describe them in terms of growing or decaying in a rapid state. Okay, you can apply it to a lot of different things. So today's main focus is going to be talking about what the functions look like, okay, like the basic standard form, maybe the parent function, okay, and how do we graph them? So how do they look in the graph? How do I know what it looks like in the graph? Okay, so features of the graph as well are included in that. All right, but before we move on to talking about all that good stuff, let's just recall the geometric series from earlier, okay, which, if you recall, has a formula, okay, a formula for finding any one specific number, okay, in the list. Okay. That formula was a sub n equals a sub 1 times r to the n minus 1. Okay, so if you remember that from the notes a couple days ago, this form is actually a example of an exponential function. So this, in and of itself, okay, is an example, okay, of an exponential function. Now I should mention before I go further, okay, that there aren't any guided notes, so you'll definitely have to try taking this on paper. Okay, please pay attention to that, and try to take as much information as you can, write it as neatly as I can. I'm going to go, in a nice order, so hopefully you guys don't get lost along the way. Okay, so this is an example of an exponential function. Okay, you've got this idea of something being raised to an unspecified power, a variable power, okay, and multiplying by some constant to give you what you're looking for. In this case, it would be the entry in the list of the geometric sequence. So let's talk about the general form, okay, of an exponential function. Okay, so it's going to be pretty similar looking, so keep an eye on that. It's going to be f of x, okay, that's the y, that's what you're trying to look for, equals, okay, a times b raised to the x. Okay, this is the basic form. This is the basic form. All right, so a here being a constant, okay, and b here also typically being a constant. Two different constants. We use a and b for that, and x, of course, being your input, what you put into the function, and that's what really makes this whole idea come together. All right, so this is the standard form, general form, okay, of an exponential function. Yeah, sometimes you might have some other things added out here, okay, possibly in plus c, minus c, etc. Okay, but I'm not going to include that here because this is the most basic of basic forms. All right, a times b to the x, and that's it. You will have to deal with c in some time, but that's pretty easy to deal with, and we'll get to that when we start talking about graphing. All right, so where a is constant, okay, b is also the rate, okay, also concerned as the rate, okay, either growth or decay. Okay, and then this is your input, of course, and here's your output. So labeling all the parts of the function there just so you know what each part means, okay, going into it. All right. Now, why is this important? Well, because I'm talking about growing or decaying. Okay, if you grow, that means your graph's going to go nice and upwards. Okay, if you're decaying, it's probably going to go downwards. Okay, and of course the sign in front, based on our transformation knowledge, could flip it upside down or what? So what? Okay, so on and so forth. But that's our basic understanding of the exponential forms. Now I'm going to come up with a couple examples to show you. Okay, a couple examples to show you, and then we're going to go to Delta Math to see those problems being done. So hang on just a sec. All right, and we're back with Desmos here. So here's just showing you what the graphs look like. Okay, you've probably seen them before. All right, but I've got this set up so that I have it y equals abx. That's my standard general form. Okay, I know I'm not using any numbers, but actually I am going to be using some numbers. I'm going to mess with the values of a and b. Right now I got them set equal to 1, which is very uninteresting. It's a flat line. And I would probably not even call this an exponential function, although even so, it is technically exponential. Okay, but it's not very interesting because anything 1 times itself is going to be 1, so that's not going to be that interesting. Now, if I change a, it's just going to move the line up and down. Okay, so that's, pretty unimpressive. I think most people don't really mind that. Now, here's where it's going to get wacky, though. Okay, here's where it's going to get wacky. I'm going to change my b. That's my rate. Remember, that's my rate from earlier. So if I change it to go above 1, that's what we call an exponential growth. That's what we call an exponential growth. And see what happens when I do that. Whoa, look at that. And the further I take it out, the closer it gets to the y, the faster it is growing, okay? And that's why we call this exponential growth, okay? It grows rapidly at a quick pace, okay? And I'm kind of showcasing that with the little slider here, okay? And even just at 3, okay? Even just 3, you see how close it gets to the y-axis, even though I'm not going that far out. This tick is going to be 5, by the way, so even at 5, I can't even see the top anymore. Now, in the other direction, if I decide to go below 1, that's what we call an exponential decay. So let's go ahead and take a look at this. Oop. All right, well, it's going to go in the opposite direction, it looks like. So kind of the same shape, but opposite direction. Not that bad, all right? So again, if you hit 0, it's going to be pretty uninteresting. But if you hit the negatives, it doesn't work. Well, why would that be the case? Well, why would that be the case? Well, there's actually a reason for that, but we won't explain that reason right away. Okay, but just know for now that b is limited to being a number greater than 0. You can't have this idea of a negative raised to some exponent in the exponential function, as it just doesn't really work, because I don't see any graph on here, do you? Okay. But if you have a 0, you do get something. It's not very interesting. But anything in between 0 and 1 will give you a decay. All right, now let's head over to Delta Math, okay, and see how this plays out with all the features we know so far, which so far is growth, decay, and the standard form. And let's put some numbers to those things. All right, I'm back with the first example here on Delta Math, okay, and it's going to be a pretty interesting one. There aren't many problems that just do with numbers. You almost always want a context for your exponential function. Otherwise, you're not really looking to get a whole lot of growth or decay of something. Okay, so we're going to be working with a lot of word problems here, so make sure to get your thinking caps on. A new car is purchased for $20,700. Okay, I'm going to underline that. That seems important. And then we know that the value of the car depreciates at 11% per year. Depreciates. I definitely want you to take a look at that, as well as the number that comes with it, 11%. What will the value of the car be to the nearest cent after 11 years? 11 years is our time. Okay, so remember that's going to be important as well. So what I've circled and underlined here are going to be important pieces for when I put together the formula. Okay. Now remember that formula, y equals ab to the x. Okay. Remember those pieces again. This is our output, so this is not changing. It's going to be y. Here's our input, so I'm not going to be changing that for the moment. I'm just trying to get the standard form so far. Okay. And then this is our constant. Okay. You can also call this your initial. Okay. Your initial. And then this is your rate. Okay, this is your rate. So remembering all that stuff, let's go ahead and take a look. I'm going to use a different color for each of them. So let's start with the constant part. Okay, in the constant department, it's going to be what's given to you in the problem. The car costs $20,700. Okay, so let me go ahead and start writing out our standard form for this function. Okay, y equals 20,700. All right, so I got my first bit done. Not a bad deal. Next part is the rate. I'm going to use green to underline that. Okay. The rate is going to be this 11%, and we know it depreciates. Okay. So what does the term depreciate mean? That means whatever you're talking about is getting less valuable over time. Less valuable. Okay. Now, something important with this idea of the exponential is that you're going to be wanting to consider this rate right here, this b, as a 1 plus or minus whatever your rate is. Okay. All right. So it's going to be minus in this case because we're depreciating. Okay. Depreciating meaning going down. So if you're talking about this, I have 1 minus 0.11. Make sure to change your percent to a decimal by moving the decimal point over 2 spaces. And if you do that in your calculator, you should get 0.89. So that's my rate. That's my b. Alrighty, so here's my b part. All right, and then I've got input and output. Now, input and output are just going to be y and x for the meantime. This is going to be my standard form, okay, my general form for the problem. All right, so when I plug in this 11 years, I'm just going to be calculating with x equal 11. So let's go ahead and do that here. I'm going to move all the way down here to do it. Y, okay, when x is 11 is 20,700. times 0.89 to the 11th power. Now, obviously, you're not going to be able to do that by hand. So, make sure you've got a nice, handy-dandy calculator. Okay. In my case, I don't really have one right now, but I can definitely pull one up. Whoa, it looks like I warped over here, but really, okay, all I did was kind of I put the calculator on the left and move myself to the right so I didn't cover it up. Now, this calculator comes with every computer, but I'm sure if you're not using your computer, you've got a calculator somewhere in there. It's actually more convenient if you have a graphing calculator, or maybe you even have Desmos to plug it in, but I'm not going to use the normal calculator here to do that. Okay, I've got 20,700, okay, and I'm going to multiply it by 0.89. Okay, now when I do this, okay, with a normal calculator, you can just count the number of times you multiply by 0.89, and then you'll be done. So this is the first time I've done it. Okay. Well, first time I do it, I have a depreciated value of 11%. Now let's do it 10 more times. Okay. If you want to count up to 11. If you don't have a specific calculator, this is the easiest way to do it. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay. So after 11 times, 11 years, okay, this is now the value of the car. This is now the value of the car. All right, near to the nearest cent, so I'm going to consider this 08 part. Okay. If you round up, it's going to be 5,744.61, so 61 cents there. And that's what I'm going to go ahead and put in the answer box. Okay, what will the value of the car be? Well, I just kind of forgot it, so let me pull it back up. 5,744, okay, got it. 5,744 and 61 cents. Okay, let's submit our answer here. And we got it right. Okay, so that's the way depreciation works, but in general, if you're talking about exponential, you're just going to have to find out what the rate is and how that adds to your 1, okay, your 100%, in order to cause a growth or decay, and then you're just going to plug in what your value is for x. If you've got a calculator, please use that. If you don't got a calculator, Desmos is fine. Okay, that totally works. But here's their explanation on it. You can always check this as well. Okay, but they kind of do it all here for us. All right, let's get to the graphing part. All right, I'm back with the graphing part of this lesson. Okay, so I've got a problem here. Graph the function f of x equals 2 to the times 3 to the x on the axis below. You must plot the asymptote and any two nodes of the whole number of coordinates. Now, what I didn't mention about the graph, but you may have seen, based on what it looked like, is that all exponential functions have a horizontal asymptote. And this doesn't have one. But I mentioned before that you might see some problems with a plus number or minus number. That plus or minus number at the end is your horizontal asymptote. In this case, there is none, so it'll be at 0. All right, I'm still going to put it there. Okay, I'm still going to put it there because they usually exist. Okay, it will give you this nice little red line you can drag up to 0, 0. Okay, if you want to do that here, along with me. And then you're going to have to mess with these 2 points. Now, when you look at this 2 times 3 to the x power, okay, you should pick some numbers that are very easy to do computationally. Things like 0. If I put 0 in for x, 3 to the 0th power is 1, times 2 is going to be 2. So I'm going to drag that here. And then how about 1? Well, 3 to the 1 is 3, times 2 is 6. So this should go right about here-ish. Okay. And it will auto-fill in the graph for you on Delta Math. Very nice of them, right? Well, this looks like a pretty basic exponential function. I think I got all the points right. I got my horizontal asymptote. I got my 2 points. I'm pretty sure I'm good. Now, if you want to check it, you can always use Desmos, okay, or pull out some more points, figure it out. But there it is. Okay, graph on a graphing calculator. It usually asks you to do that, but there you go. There's your 2 points. So find some points just by plugging in some values. I'm sure you can do that and figure out where the asymptote goes. That comes from the C part. Okay, let me get you another problem for you, okay, to help you out. This is a little more complex of a problem. Okay, this one doesn't have just the basic x and the exponent anymore, but you're going to see these problems potentially, so I better do it for you. Okay, before I get it to you. Now, in this case, I'm not going to worry about this x plus 5 part for right now. I'm going to worry about this -3 sticking around. Okay, that's going to tell me my horizontal asymptote is going to be at that area. Okay, the -3 right here. All right, so there's my horizontal asymptote. And then I don't actually have a number multiplying out against this -2, which is my rate. So I'm actually going to say that there is no a for this, but that's all right. I just need to plug in some points. Okay, just need to plug in some points to figure it out. Now, if you plug in 0, x plus 0 plus 5 is going to give you 5. It's a kind of a bigger number. So in this scenario, try to pick some numbers that are easier to work with. In this case, I'm going to pick -5. So I'm going to go drag my point out to negative 5 first, and then I'm going to evaluate negative 5 here. Okay. If I say x equal to negative 5, negative 2 to the negative 5 plus 5 power minus 3. Well, this is 0, so that kills this whole thing into just 1. But it's going to be negative 1, careful here, because that negative sign is outside of this outside of the exponent. Okay, so negative 1 minus 3 gives me negative 4. So that's when x equals negative 5. Okay, so on my graph, negative 5 for x, negative 4 for the graph. All right, so far so good. Right now I don't have a graph because the other point is not quite there yet. How about the other way around? If I go ahead and just pick another one, I'm going to pick x equals negative 4. X equals negative 4 will give me this negative 2 to the negative 4 plus 5 power minus 3. Well, this is going to be 1. 2 to the 1 is 2. Negative applied to that is 2 minus 3. Okay, and then you got negative 5. So I'm going to move this dot over to negative 4, negative 5, and there we have it. Okay. Now, does it look right to you? Maybe. Okay. If you consider the negatives out front, use your transformation knowledge once again to think about, hey, transformation with a negative sign out front, that's a vertical flip. We call it a vertical flip. So that looks right to me. Okay. And let's go ahead and put this baby in. Ta-da! Real easy. Okay, so pick out your horizontal asymptote, really simple, and then plug in some points, and that will let you graph the exponential function in our module. That's everything I got for today's video. Okay, it's a little bit lengthier, and it's not really concrete because I don't have any guided notes for you, but make sure to watch it again, pause it here and there if you need help on the video, and I'll see you guys in class.